Okay, so we're going to begin our rotational motion review, first talking about rotational kinematics. And as you remember, for rotational kinematics, we have 4 new equations, but they're really just the same as our linear kinematics equations. Alright, so there are the 4 equations, and like I said, they're exactly the same as the regular kinematics ones. We just have delta theta instead of delta x. We have omega initial and omega final instead of VI and VF. And we have alpha instead of our acceleration. Nothing else has changed about them though. In terms of directions for rotational, we talk rather about up, down, left, right. We talk about clockwise, and we talk about counterclockwise. And although it doesn't actually matter which one you pick to be the positive, just like regular directions, typically clockwise is considered to be the negative, and counterclockwise is considered to be the positive. All right, next we have our equations for converting between the two. So we have delta x is equal to r delta theta, v is equal to r omega, and a is equal to r alpha. Each time radius is the key. Now this comes into play in 2 situations. The first situation when we can use these is if we have an object rolling smoothly along the ground, and we're thinking about the velocity of its center of mass compared to its angular speed, or the acceleration of its center of mass compared to its angular acceleration, and so forth. The second time when we're going to use this is when we're thinking about a rotating object, and we're thinking about a point on that rotating object and the velocity, the tangential velocity of that point, or the tangential acceleration of that point compared to the angular velocity or angular acceleration. So those are the 2 situations where those equations come into play. Moving on to motion graphs with rotational motion. So on an angular position versus time graph, the angular velocity is simply going to be the slope, just like it is with a regular position versus time graph. And the angular acceleration is going to be the curvature. Okay, so we're looking at whether it's concave up or concave down. All right, moving on to the velocity versus time graph. In this case, the angular displacement is going to be the area under the curve. We're going to integrate just like we did with a regular velocity versus time graph, and the angular acceleration is now going to be the slope. Okay, and all the other ideas apply about when we're speeding up, when we're slowing down, and so on. All right, but these are really the key ideas that you have to know. All right, moving on to torque, which was an important concept in this. This was our rotational equivalent of force, okay? And it results when we have a force exerted, an off-center force being exerted on an object. And it's going to be measured in Newton meters. Now the next thing is our torque is a maximum when our angle is 90 degrees. And our torque is 0 when our angle is 0 or 180. All right, so we have to exert this force perpendicular to that r. Okay, so if we have a beam here, we have to exert a force like this to lead to a torque. If we exert a force like that or like that on the beam, assuming that this is the pivot point, there will be no torque. All right. Lastly, we want to make sure we consider our directions. All right, think about whether or not it's rotating or causing clockwise or counterclockwise rotation. All right, moving on to torque, which was an important concept in this. This was our rotational equivalent of force, okay? And it results when we have a force exerted, an off-center force being exerted on an object. All right, so it results from an off-center force being exerted on an object. All right, moving on to moment of inertia. Moment of inertia is going to be the rotational equivalent of mass. All right, in other words, how difficult it is to make something rotate. Okay, that's really what moment of inertia represents. Moment of inertia is measured in kilogram meters squared. Okay, and the factors affecting it, so obviously mass is the first factor that's going to be affecting it. The size of it matters, but really the big thing is the distribution of the mass. All right, that's really what affects moment of inertia, and how far the mass is from the point where we're rotating. And the further away mass is, the greater our moment of inertia. All right, so let's move on to talk about Newton's laws for rotation, which are essentially the same as Newton's laws for just in general. So the first is that we have unbalanced torques cause angular acceleration, all right, just like unbalanced forces cause linear acceleration. Our second law that we have is our equation. Instead of sum of the forces equals ma, we have sum of the torques equals I alpha, our moment of inertia, times our angular acceleration. And lastly, and we don't use this one that often, but we do have the idea that about a given pivot point, objects exert equal and opposite torques on each other. Okay, so that is the third law, although like I said, we don't use that one quite as much. Some tips here. One of the important things for these problems is to draw a free body diagram and consider where those forces act. All right, that's a really big thing because that affects the torque. All right, next we're going to set up sum of the torques equals I alpha for all rotating objects, and we're going to set up sum of the forces equals ma for all objects that are just undergoing an acceleration. All right, and there will be situations when we have both, and we've seen that with the pulley falling and the masses or something along those lines. And we want to remember to use our links. All right, so a big one that we use a lot here is A equals R alpha to connect the two. And this again would only be if we have both, but that situation could come up. All right, moving on to equilibrium. These situations where the object's not moving, so equilibrium occurs when our acceleration is 0, which means sum of the forces equals 0, and this is our new one in the rotational world. Angular acceleration also equals 0, so the sum of the torques equals 0. And usually this is going to be the more useful thing. All right, so for these equilibrium problems, we're going to start as always with our free body diagram, and sum of the torques equals 0. Few other things to keep in mind. We can pick any pivot, all right, but a good one, all right, would be to pick one where there is an unknown force that we don't care about. All right, that makes our life easier because if that force is acting on the pivot, there is no torque created by it, and so it eliminates that unknown force. Something else to keep in mind, the force of gravity acts in the middle, or at least we can treat it as acting in the middle. It technically acts everywhere, but in the middle of uniform objects. Okay, so if we have a mass, say for our beam or whatever is being balanced, that force is going to act in the middle. And really I should add in here that it acts at the center of mass. Now for a uniform object, that's directly in the middle, but that actually leads us into our next idea, that objects balance. All right, and if we're just looking for where an object will balance, objects balance at their center of mass, at that average location of the mass in the system, because that's where the force of gravity acts. All right, and so if we put the pivot where the force of gravity acts, then there is no torque created by gravity, and the object's going to balance. All right, moving on to rotational kinetic energy. Rotational kinetic energy is the kinetic energy of rotating objects. All right, and a big idea here is so obviously a moving object has regular kinetic energy, a spinning or rotating object has rotational kinetic energy, a rolling object rolling smoothly, all right, is going to have both kinetic and rotational kinetic, both of those energies. The formula that we're going to be talking about in this unit, so rotational kinetic energy is 1/2 I omega squared. We also have our linear version of work. Instead of force times displacement, it's torque times angular displacement. So same basic idea here. And some tips, really there's just one big thing to keep in mind here, and that's this idea of rolling smoothly. Okay, and there's a few important ideas from this. Number one, if we are rolling smoothly, it means we can use V equals R omega. That's an important idea. Number two, it means that there is no work done by friction. All right, and really, what it comes down to is if it's rolling smoothly, the object's not actually sliding relative to the surface, so friction can't do any work. Okay, what actually happens is FF provides the torque needed to give the object rotational kinetic energy or take away the object's rotational kinetic energy. All right, and we've seen lots of examples of this, of what happens when we have a frictionless ramp. And basically, the object doesn't change its rotational speed. If it's already rolling, it keeps rolling. If it's not rolling, it won't start rolling. Okay. All right, angular momentum. This is simply the angular equivalent of momentum, obviously. And we have a few formulas associated with this. The first is just what angular momentum is, L equals I omega. The second is that angular momentum is conserved, assuming no outside torques. All right. And we can combine those first two. So if we're dealing with a single object where our moment of inertia is changing, all right, this is our equation. So this is when we have a single object where the moment of inertia is changing. So those were the three big ones. Obviously, we could set this equation up normally like we would, where there's two individual objects rotating and then they collide or somehow interact, and we have a new angular momentum. A few tips with this, all right? Keep in mind that L is conserved if there are no outside torques, right? That is the big qualification for this to be true, or no net outside torques, right? The next thing is we're going to use this equation when we have a single object and its moment of inertia is changing. So really, this is simply the angular momentum for a single object. And what we can use that to do is analyze the situations when that moment of inertia changes. The figure skater bringing her arms in is a classic example that we've talked about.